Welcome to what is almost our last video lesson. So today we're going to look at allotropes of carbon. So by the end of this lesson, you're going to be able to recall some allotropes of carbon. Don't worry about what allotropes are, we'll cover that a little bit later on. We're going to look at both the properties and the structures of simple covalent molecules and giant covalent structures, and you need to be able to describe the basic differences between the two. And there'll also be a research task for you at the end of the lesson. So if we think back to our previous lesson on covalent bonding and covalent compounds, you should remember that covalent bonding only happens between two or more non-metals. And this almost always results in a small molecule made up of only a few atoms. And this is what we call simple covalent. So examples of a simple covalent compound would be things like O2, which is two oxygen atoms bonded together, or carbon dioxide, which is one carbon and two oxygens bonded together, or ammonia, which is NH3, which is one nitrogen surrounded by three hydrogens. So these are all examples of simple covalent compounds. And remember, these are held together by covalent bonds, which we can show as a simple line between two atoms joining them together. And covalent bonds are very strong and difficult to break. So once two or more atoms are bonded together covalently, they tend to be quite difficult to separate, and those bonds are quite difficult to break. Now, in the real world, it's very unlikely that you would get one individual covalent molecule on its own. It's much more likely that you would have a group probably made up of millions or billions of molecules all in one area together. So as an example, O2 oxygen, you would find that in the atmosphere, and obviously the atmosphere is composed of trillions and trillions of O2 molecules all in a group together near each other. And when you have a group of simple covalent molecules, each molecule is attracted towards its neighbours, so they want to try and stay together. And we call that force that tries to hold together groups of covalent molecules intermolecular forces. And intermolecular just means in between molecules. So inter means in between and molecular means about molecules. So an intermolecular force is a force that exists in between separate molecules. And these intermolecular forces that try and hold groups of covalent molecules together are quite easy to overcome. Those forces are quite weak. So it's quite important that we don't get confused between the strong covalent bonds that actually hold each individual molecule together and the weak intermolecular forces that try and group all of those molecules and hold them together in one group. So as an example, if you think about carbon dioxide gas, we know that carbon dioxide is CO2, which is a simple covalent molecule, and each carbon has two double bonds holding on to two oxygen atoms. Now, if you heat up carbon dioxide, you give each molecule more energy and they start to separate and get further apart. We're overcoming the weak intermolecular forces that try and keep all the CO2 molecules together. But when we overcome those weak intermolecular forces, we're not doing anything to the actual covalent bonds that hold the oxygens and the carbons together. So think also about water, H2O, which is another simple covalent molecule. When H2O is in its liquid form, which we would call water, the molecules are held quite close together by the intermolecular forces that attract them to their neighbours. If we add energy by heating water, we can evaporate it into a gas. And when we evaporate water into a gas, the energy that we've added by heating it is used to overcome the intermolecular forces, and the molecules start spreading out as they become a gas. But whether H2O is a liquid or a gas, that has no effect on the bonds between the hydrogens and the oxygen. Those covalent bonds remain intact even if we boil a liquid and evaporate it and turn it into a gas. Okay, let's have a look at ethene, which is another example of a small, simple covalent molecule. An ethene, which you can see on the left of that diagram, is made up of two carbon atoms with a double bond between them and four hydrogen atoms which are bonded to the carbons with a single covalent bond. Now, some simple covalent molecules, like ethene, can actually join together with other ethenes and form what we call a long chain. So one ethene on its own we describe as a monomer, and mono simply means one. So ethene is a monomer because it is one ethene on its own. But it's possible to take lots of ethenes and to break that double carbon bond in the middle and form a long chain molecule out of many, many ethenes. And that chain can be thousands of ethene molecules long. And when we form a long chain out of many monomers, like ethene, we call it a polymer. Poly just means many. And when we name the polymer made out of joining lots of ethenes together, we call it poly for many, ethene because it was made out of the monomer ethene. So lots of ethenes joined together in a chain is called polyethene or polythene. And you've probably heard of polythene. So, for example, a polythene bag that you might get from the supermarket or plastic drinks bottles are all made out of polymers that are made up by joining together many, many monomers. So let's have a look at some giant covalent compounds. So one interesting example of a giant covalent compound is diamond. Because you may not realise that a diamond is made up of only carbon atoms. Now you might remember that carbon has the atomic number 6, which means it has 6 protons, and it also has 6 electrons. And because 2 are on the inner shell, the outer shell of carbon has 4 electrons, so carbon always wants to make 4 bonds. So it's possible to take many carbon atoms, each of them looking for 4 covalent bonds, and you can bond lots of carbons together in a giant carbon lattice, where every carbon bonds to 4 neighbouring carbons. And you can see that in the picture on the screen. Now, because covalent bonds are so strong and difficult to break, and because carbon can bond to 4 neighbours in 4 different directions, this makes a diamond the hardest material known to man, because whatever forces you apply to that diamond, it's very, very difficult to break that network of covalent bonds that exists between all of the carbons in the lattice. And closely related to carbon is another substance that you probably heard of, graphite. And graphite is what is actually found in your pencil lead. So the lead in your pencil is not actually made out of lead at all, because lead is poisonous to humans. We call it lead because it used to be made out of lead, but a modern pencil is actually made of graphite. And graphite is another substance that is only made of carbon atoms. But instead of bonding to 4 neighbours, the carbon atoms in graphite only bond to 3 neighbours. We could also have carbon powder, which is similar to coal that you might get out of the ground, and this is also made of only carbon atoms. But these are not arranged and bonded as neatly as graphite or as diamond. So because all 3 of these examples are only made up of carbon atoms, they all have the chemical formula C, because carbon is the only ingredient, the only type of atom in that substance. But the way that the atoms are arranged and bonded with each other changes the properties and the characteristics of that substance. And these are called allotropes of carbon. And an allotrope is just a different structure that's different because of the way its atoms are bonded and arranged. So on this slide, you can see at the top there 4 different allotropes of carbon. So diamond we've already talked about, graphite we've talked about, and there are 2 more there. There's graphene, and there's what we call a fullerene, which has the chemical formula C60. So that is made up of 60 carbon atoms bonded together in a ball shape. So your task for the rest of this hour is to take each of those 4 allotropes of carbon and to do your own research on those allotropes and to make a cue card for each of them. So each of your 4 cue cards should contain the following information. You should have the name of the allotrope. You should draw a diagram and describe the structure. You should find out the properties. For example, can it conduct electricity? And you should find 1 or 2 uses for that allotrope of carbon. And if you have time, your Warwick Star Challenge is to explain the properties and uses of each allotrope in terms of their structure and bonding. So why does the structure and bonding of a diamond make it suitable for the uses that we have for diamonds? It's going to be quite difficult for you to show me your cue cards that you've made before we get back into school. So I'm going to ask you to hold on to them, make sure you don't lose them, and bring them into school when we're back in next week, and we'll use them in a lesson once we're back in the classroom. Okay, good luck with that task. Any problems, drop me an email and I'll speak to you soon.